Not that one. Un momento. My computer does not want to open things. Trying to shut down extra stuff that's hogging memory. There we go. Okay, so this is another old people data set, but it's not the same old people. Different story. So these are data from the octogenarian twin study of aging. I put a link in case you're curious about this. I've used that data set for a number of class examples. I am going to be examining 3 outcomes over time that are supposed to be consistent with a latent measure of cognitive functioning. That's my goal here. So I have block design, which is like a matrix reasoning kind of task, digit symbol substitution, which is a working memory task, and prose recall, which is measuring memory, longer-term memory, slightly longer-term memory. And their patterns of correlation are consistent with the idea that it's a single factor underlying them. For 3, you can't test whether that's true if you only have 3, but you can once you get multiple occasions in the model. So we'll do that as one of the first things. So I am shortcutting this example in ways that would be unacceptable if this were a real data analysis, okay? Because this is already hard enough. I'm only using 4 of the 5 occasions because the 5th one had so much missing data that it was causing problems. I am pretending that the occasions are completely balanced. So it's just going to be like time 1, time 2, time 3. And in the data set, there is some unbalance as well. I'm also completely ignoring the fact that these are twins. That's the biggest one. Because a 3-level model version of this was not happening today or ever. It's possible, though. This analysis, then, is going to have lots of pieces. We'll be in this handout for a little while. Step 1 is to figure out whether there's evidence that it looks like there is a latent factor operating here. So does the model fit if I have a latent factor for each occasion? 4 occasions. Next layer is testing what is known as longitudinal invariance. So do the indicator factor loadings, intercepts, and residual variances function the same way over time? Can I force them to be the same over time and not hurt the fit of the model? That's the question. And for those of you who are like, didn't we do that in the SEM class? Yes, we did. It's coming back. It's the exact same set of comparisons where we're checking for not worse at each stage for the same exact set of reasons. If you're interested in fitting growth models, you absolutely need to worry about this. It makes 0 sense to not have constraints over time, because then your change is happening at both the indicator level and the latent trait level, and that's not what you want. So we have to have at least partial longitudinal invariance for this to work. Once we have that, then we can look at whether higher order factors of intercept and latent basis change, we're going to do that one here, can describe the pattern of means, variances, and covariances in the latent factors. So the structural model is what we're focusing on at that point. Also known as curve of factors, and I have a note here, I added the alternative in one final last set of models. All of the original source files for this, we show what the folder looks like. Come on. In the download that goes with this, you have all of the original input files and all of the output files. You don't have the data, though, because at least I think you're not supposed to have the data. I think I took it out because it's real data and I would get in trouble. So if you want to follow along with those files and make notes in them, if that's easier than working from the handout, knock yourselves out. All right, step 1, configural invariance. We are in wide data, okay? So this is single level SEM. I have an ID variable for case here. I have age at time 0 still in the data set, and then I have block 1 to 5, digit 1 to 5, and prose 1 to 5. So note you don't have to write these out. M+ understands that this means prose 2, prose 3, prose 4, prose 5. It will not do that kind of extrapolation unless the last one is what it's paying attention to. So if I named these some other way, like if I add a letter, it's not going to understand now. So naming your variables so that you can abbreviate your code is a nice feature when it works. Here's my model. I stole this picture from the book chapter that I assigned for this unit. So this picture works just fine, except for a few things. I only have 3 indicators per factor. So I put an X here, meaning this doesn't exist. And since they punted too, this is time t. So that means there's an implicit like stuff in the middle here that we're skipping over. So I have 4 occasions, meaning I'll have 4 latent variables. At each occasion, I have the same 3 measures contributing to that latent variable. So the latent variable is predicting the same 3 things. I also identified the model differently than them, so I'm setting it up so that I have variances of 1 rather than having them be estimated, means of 0. And that's why I have that thing being blocked. And then I have covariances. The 2-headed arrows here are all related to each other. So this is what is attempting to be accomplished with the code. Now here's how we do it. So I'm not that creative when it comes to naming things. T1 means the first occasion. And I am writing all the stars out to be explicit, but you don't actually need to write them. It is assumed to be estimated by default. So I am asking for factor loadings here to all be estimated. So this has no constraints on it. All possible loadings are being estimated. How many do I have here? Got 1 vote for 4. How many loadings do I have here in total in what I've highlighted? It's more than 4. We got 1 vote for 12. Yeah, at this stage it's 12 because I have 4 occasions times 3 measures. And note they all have 5 letters. See how pleasing this is? Now, because this is not a growth model, all right? This is just a regular like factor model, confirmatory factor model. I have intercepts for my indicators. So each of these down here gets its own predicted outcome when the factor predicting it is 0. That's what the intercept means in this context, just like always. Likewise, I have all possible residual variances. So in total, how many intercepts do I have? It's 12, 1 for each variable. How many indicator residual variances do I have? 12, yes. I also have specific residual covariances for the same indicator over time. So this looks like it's correlating it with itself, but what this does is all possible. So block at time 1 gets to be related to block at time 2, gets to be related to block at 3 and block at 4. So because it's the same measure, it's reasonable that there would be some relationship, so we just let that be in here. And these stay the whole time and we don't touch them. I am choosing a method of estimation that standardizes the factors. So I'm fixing all of their means to 0, and I'm fixing all of their variances to 1. So the scale of this is that they're not comparable at this point. Like this is essentially the z-score thing that I told you not to do. But that's because they don't need to be comparable. We're going to make them comparable in the next sets. We're just testing whether a 4-factor model is supported by these data. That's what we're doing. And all possible factor covariances are in here as well. Now, if you haven't had SEM before, this is going to be like, what is all this nonsense? But if you have, then this will look familiar. So the first thing it's going to tell us about is how wrong our model is relative to the data. So I'm pretending I have balanced data, right? I told you that? Okay. What's the answer key? What's the rightest model that I could have for my 4 occasions from last semester? Unstructured on the variance side, right? And on the mean side, what did we call it? Starts with an S. Saturated. Yep. That is the log likelihood for each one. That's what it's giving you. Is here is the tallest your data can possibly be. That would be the same exact value if I use mixed or Elmer, or not Elmer, GLS and R to estimate a saturated means unstructured variance model. That's what this is. It's called the saturated model in this notation. Now my model is this one. The question is, how much shorter is my model? What is the difference between these two? In this example, I am using MLR estimation. That means robust maximum likelihood. That is supposed to correct fit statistics and standard errors for deviations of multivariate non-normality. That means that likelihood ratio tests are not conducted the same way. They're conducted incorporating this number right here, which is a scaling factor. So this number provides essentially an index of how not normal it is, where 1 means perfectly multivariate normal. So these data aren't too bad, but I tend to use this sort of as a default because then I don't have to worry about violations of normality affecting fit statistics as much as I would otherwise. So unfortunately in M+, there is no direct way that I know of, and I've looked, trust me, to do likelihood ratio tests. So if you were to run the same model in lavaan and R, you could use the ANOVA function to do likelihood ratio tests, and it would do the right ones. Instead, I had to build a spreadsheet. So in the download packet, Ahmed's like, what? Like, I know, I had to hand enter a whole bunch of numbers. It's terrible. Do not recommend, but this is what I'm stuck with when I use M+. So each of these is a likelihood ratio test. So the first thing I'm going to do, for instance, is compare the configural model, to the next metric model for loadings and whatnot. So essentially what is happening in this output for the chi-square is that it's doing that for you. So this chi-square test of 27 is how much worse our model fits than the perfect saturated model. We did this last semester as the idea of testing absolute fit. But because we did it in REML, we did it for each side of the model at a time. We tested deviations to the fixed effects for the means, and we tested unstructured versus whatever random effect structure we came up with. So 30 degrees of freedom means I could have estimated 30 more parameters in this model. P-value is non-significant. Is that a good thing or a bad thing in this context? It's a good thing, because that means that my model is not worse than perfect. So it's a backwards way of thinking about hypothesis testing. Non-significance is good. So this means that I have evidence that my 4-factor model is supported by the data, that the pattern of correlation in the data is well represented by the implied pattern of correlation by this factor model. That's what I learned. Then we get additional fit statistics that tell us the same thing using different indices. RMSEA is how wrong you are per degree of freedom left. It's 0, like this is as good as it gets. CFI and TLI compare your model to a different standard. How much better is your model than the worst possible model that says you have no correlation whatsoever? And that is perfect. 1 is as high as CFI can go. TLI can actually go above 1. You can ignore this one. This is a test of saturated versus worst. None of them involves your model. And that one is how wrong are you on average in a correlation metric. And 0.01 is pretty darn good. So I'm happy with this. This is like the best fit I've ever seen in real data. I know. So then the output. The buys are factor loadings. So by the way, this is me being nice. M+ does not label stuff for shit. So I have similar looking loadings over time, I would say. Like these are all in the neighborhood of 6, 10 here, 10 here, 11, 12. These are clearly outcomes on different scales. So it's hard to have a sense as to whether these are strong relationships without knowing what the units are. They're significant, but we don't know that. We can look at the standardized solution to get a sense of that if you want to. Factor covariances, in this case, these are correlations because the variances of the factors are all 1 and the means are all 0. So it looks like there's pretty high relationships over time. Like there's a lot of stability in how this trait stacks out across occasions. We don't yet know if there's change, though, because we set all of the factors to have a mean 0 and variance 1 for identification. That won't work if we're interested in change. So we're not doing that yet. Okay, this is just the factor side. Here are the residual correlations, or covariances rather, of the same indicator with itself over time. Leave those in the model. Factor means are all fixed to 0. Intercepts. These are the expected outcome for each of my observed variables when the factor predicting it is 0. The factor means are 0, so essentially these are the means of my my intercepts. So I can get a sense as to how things are changing by looking at these. What do you think? Is block design going up over time, down over time, or staying the same? Yeah, it's going down a little bit. How about digit span? Yeah, or digit symbol. And pros recall? Kind of all going down. So this is sort of conceptually step 1. Like all of the indicators you would want to be heading in the same direction for any kind of common latent trait to make sense. If you have some that are growing and some that are declining, like you're done. Like stop. It's not going to work on a longitudinal model. But these are all heading in the same direction. We'll see. We have to see it to the same extent. And then variances here, all fixed to 1. These are leftover variances. So these are the amount of each of these variables that is not predicted by the factor. All right. Now, I'm not going to make you do this today. I promise. We're going to leave. But I just want to tell you, I'm trying to be nice. I'm using colors to highlight the part of the code that's changed, because it's too damn hard to keep track of otherwise. So if you don't have a color printer and you're a paper person, I apologize. But colors will help us. So we're going to layer on these constraints one at a time, test invariance, and then we can build a growth model. Because then we will have evidence that it is the same trait over time, which is a prerequisite to seeing that trait grow or decline. All right, questions? If you have not had factor analysis as coursework or haven't seen it before, I would recommend visiting on lecture 0 of this class. I listed out specific examples and stuff from the SEM class that might be good to review. So if this is not familiar to you, it might be useful at some point to go over that. But again, not making a homework out of this because I don't want it to be unfair. All right, any questions before we call it a week? Since it's Thursday. No, we're good? Good for now. All right, then please work on your outlines. Let me know if you need help or want to talk, and I hope to see you next week. Have good weekends. Bye for now.